Hi. So for my Unit 2 project, the problem I picked was this. The combined perimeter of an equilateral triangle and a square is 10. Find the dimensions of the triangle and square that produce a minimum total area. So this is going to be what's called an optimization problem, where there's infinite amount of right answers, maybe not infinite, but there's a lot of right answers, but we need to find the best one. So we're going to be finding the minimum total area, even though many dimensions could get a perimeter of 10. So I'm going to write a notice list. We start with a notice list. The triangle has 3 equal sides because it's equilateral. The square has 4 equal sides. That's the definition of a square. So we can rewrite the triangle perimeter as 3t, t for triangle, and the square perimeter as 4s, s for square. Therefore, the total perimeter is 3t plus 4s, but we know the total perimeter is 10, so we can write 10 equals 3t plus 4s. Now we know the area of the square is s squared, that's pretty easy, and the area of the equilateral triangle is square root of 3 over 4, t squared. I'm just going to run over through this really quickly so you can understand why that's the area. Say we have this equilateral triangle. Each side is length t, and each angle is 60 degrees because that's how equilateral triangles work. So the area of a triangle is base times height over 2. The base is t, we know that, but we don't know what this height is. So to find the height, we're going to split the triangle in half, like so, right? We have, now the base is t over 2 because it's half of the base. The hypotenuse is still t because this side is t. And now we have this length we don't know. Now the important thing is now this is a 90-degree angle. This is still 60, but this became 30 because we cut the angle in half. Now we know a 30, 60, 90 triangle is the base is x. This is 2x, right? We have t over 2 and then t, so it's x and 2x. And the height is x root 3. So now we can do root 3 times t over 2. And then you have root 3 times t over 2 is your height, times your base of t, and you get t squared root 3 over 2 divided by 2, and you would get t squared root 3 over 4. So that's how we get the area of an equilateral triangle. Okay. So here are the steps to an optimization problem, specifically this type. We're going to start by writing down the basic info we know, right? They gave us the perimeter, the what shapes we have, that's basic stuff. Now the second part is we set one variable in terms of the other because we can only have one when we make our equation. I'll explain it in a second. Plug that into the other equation. So the way optimization works is you have a equation and you find the minimum or the maximum of it. So we're going to plug our variable into the equation. I'll explain that. Graph that equation. We're going to find the minimum. In this case, yeah, the minimum. Then you're going to define what your x and y mean. You're going to understand your answer to the question. You're going to answer. You're going to answer it, and then you're going to check with other possibilities to know for sure you're right. So we're going to start with step 1. Write the basic info. I wrote 10 equals 4s plus 3t, right? That's what they give us. And that the total area is s squared plus square root of 3 over 4 t squared. So theoretically, we can graph this because we're trying to find the total area. We should find the minimum. But you can see we have s squared and t squared. We can't have s and t. That brings us to step number 2. Write one in terms of the other. And that's what we're going to do right now. I wrote 10 equals 4s plus 3t. We're going to solve for s right now. So s is 10 minus 3t over 4 is another way to write it. You can see how I did that algebraically. So therefore, instead of writing total area equals s squared, I'm going to write 10 minus 3t over 4 squared. And then still the plus square root of 3 over 4 t squared. So it's the same thing, but I substituted this for s. Okay, now I'm going to take that function. And I'm going to set y to total area. So this will be y equals, and I'm going to set x to triangle side length. So x is going to be triangle side length. So I'm going to graph that. And you can see here's my graph. I rewrote the equation in all these different ways. You can do that, but it's not helpful. And our minimum point is 1.883. Okay, and 1.883 comma 2.719. So this is the hardest part. The biggest, easiest way to make a mistake is if you didn't make it clear. I made it clear what my x and y were, right? Total area for y and triangle side length for t. But if you got confused and thought that this was a square side length, you'd get everything wrong. So that's the important thing. Really be clear. That's why I have a whole step, which is define x and y, so you really know what you were doing. So In that step, we can say triangle side length is 1.883, total area is 2.719, and then we know the triangle side length. So for the square, I just plugged our triangle side length 1.883 into this, and I got the square side is 1.088. Okay, now we're just gonna check our work because we got the correct answer. Minimum, it looks right, but we just want to make sure it actually gets a perimeter of 10, and then we're gonna check an upper bound and lower bound. That's another great way to check the work. So first, I wrote 10 equals 4s plus 3t. Now I plugged in 1.088 for square side length and 1.883 for triangle. I did the math, and I got 10 equals 10.001. We're going to count that as a check because if you can tell, Desmos only rounds to the nearest thousandth. So we're correct, even though it's off by 1,000. Okay, now we're going to check an upper bound, right? Our triangle side length is 1.883. What if it was 2, which is a little higher? Then the square would be 1, which is a little lower, but the square side length would be 1. We did the math. Total area is 2.732, which is higher than 2.719. So we still have the minimum answer. This is still correct. Now what if we did a lower bound? We did 1.5 instead of 1.883. Then the square side length would be 1.3575. You do the math. And then the total area of this dimensions would be 2.865, which is higher than 2.719. So we have the correct answer. Triangle side should be 1.883. Square side should be 1.088. And the total area will be 2.719. Okay, so for making it harder, I thought, square and triangle are cool. They're cool shapes to have, but what if we did a little more difficult? What if we did an octagon and a circle? Square and triangle are the two most basic shapes, two most basic polygons we could have. So I thought, what if we take a much more complicated polygon, an octagon, and a circle? Because at first I thought you couldn't do it with a circle. It's different with number of sides, but I realized you can. It's just completely different. You need to do it in terms of the radius. So just an added level of challenge. It's something different. So it'll be pretty cool to look at. Okay, I said we have an octagon and a circle's perimeter and the circle's circumference, but their total perimeter is 10, and we need to find what dimensions make the minimum total area. Same problem, but much harder shapes. Okay, first we know the octagon has 8 equal sides, and I wrote the circle has one side, like the circle's circumference is determined by the radius. That's the important part. Alright, we could say octagon perimeter is 8s, and the circle perimeter is 2 pi r. I think we know that. So the total perimeter is 8s plus 2 pi r, or we could say 10 equals 8s plus 2 pi r. And then we're going to say the circle area is pi r squared. Everyone should know that. And the octagon area is 2s squared times 1 plus root 2. I'm going to explain that real quick. So take this octagon I drew. Now everyone should know an octagon has 8 equal sides and 135-degree interior angles. That's the definition of octagon. So look, I rewrote this. I wrote each side length as s, just to give it a variable. And you see how I drew these lines? So you could say, you could have 2 trapezoids. This is trapezoid, and a rectangle. But I'm dividing into 4 triangles, 4 equal triangles, 4 equal rectangles, and 1 square. You can divide up. And the important thing here, I'm not going to explain the whole math to get this formula, but the important thing is how we get the root 2. Basically, if we draw this line, this is a 90-degree angle. 135 take away 90 is 45. So this is a 45-degree angle interior, and this is a 45-degree angle. So we have a 44, 45, 90 triangle right here. And 45, 45, 90 triangle, both sides are x, and the hypotenuse is x root 2. But in this case, our x root 2 is the variable s. So you do x root 2 equals s, and x equals s over root 2. So that means this side is s over root 2. This side is s over root 2. This is s over root 2. Same with this side, same with this, same with this, same with this, same with this. So that's how you start doing the math. And if you did all the math, you would get this equation, 2s squared times 1 plus root 2. I just wanted to show how the relationship works. So we have the same 8 steps. I'll just go over it more quickly. Starting with basic info, 10 equals 8s plus 2 pi r. Total area is 2s squared times 1 plus root 2 plus pi r squared. Notice again, we have an s and an r, so we need to eliminate one of those. You could do either way, but I think it's better to figure out what r is in terms of s. So I did the math, 10 equals 8s plus 2 pi r, and r equals 5 minus 4s over pi. So I plugged that in. I wrote 2s squared times 1 plus root 2 plus pi. Instead of r, I wrote 5 minus 4s over pi squared. Another cool thing to know you have an optimization problem is when you have like this balance of things. Like here, as like this s is growing like squared, but here we have a fraction with s. So that's how you know there's like two sides to the optimization. So as one thing goes up, the other thing goes down. So I graphed that equation, and here we go. The minimum is now 0.642 and 3.873. And again, I wrote our y was total area, and this time our x was octagon side length. So our octagon side length is 0.642. So, sorry about that. Okay, and then our total area is 3.873. So then I plugged in octagon side length to 5 minus 4s over pi, and I got the radius is 0.774. Okay, that's our answer. Now we got to check our work, right? First, I'm going to make sure that gets a perimeter of 10. So I do 10 equals 8 times 0.642, the octagon side length, plus 2 pi times 0.774, the radius. And then I did the math. I got 10 equals 9.999, which is correct, again, because Desmos doesn't figure out the whole decimal just to the nearest thousand. Okay, so our answer is correct. Now let's see if it's the best possible one. I wrote side length 0.74, radius 0.642, and our total area is 3.991, which is higher than 3.873. And now we have side length is 0.5, and radius is 0.995, which is, so here we did the upper bound, right? We did a higher side length, and here we did a lower bound, a lower side length. And our total area is 4.072, which is still higher. So we have the correct answer. Octagon sides are 0.642, circle radius is 0.774, and combined area is 3.873. So thank you. I hope you learned something about optimization problems. I hope you got to see a much harder problem from our homework. I thought it was super cool that we can do it with all these different variety of shapes, like with circles. I'm sure you could do trapezoids, other things, but I made it harder, and it was a lot of fun, so thank you.